Black holes are like space's mysterious riddles, with super strong gravity that can twist and trap even light itself.
Black hole is a region of space where matter has condensed to such a high density that the gravity at its surface is so high that you cannot escape it, even at the speed of light.
They're all over our galaxy, and the one at the Milky Way's heart is a whopping 4 million times bigger than our sun. When you're hunting for a black hole, you look for things zooming around it crazy fast. But the real puzzle is figuring out where they come from and how they fit into the cosmic picture. Now picture this. Scientists have peeked inside a black hole. Can you believe it? The big question is, what did they find in there? Is it as spooky as we've always imagined? Get ready to dive into the epic adventure of how scientists cracked open the mystery of black holes, revealing the mind-boggling secrets hiding within. Let's get started. The public and scientists alike have long been captivated by the celestial phenomena known as black holes. Time is seen as a fourth dimension that is inextricably related to space in Einstein's theory of relativity. Here, mass induces a curvature in space-time rather than a force in the traditional sense, which is what we call gravity. Think about a trampoline weighed down by a bowling ball. The bowling ball and other tiny items are drawn to the trampoline because the surface bends under the weight of the ball, producing a depression. Because of their infinite density, black holes create a gap in space-time that can never be filled. Gravitational fields are mysterious and powerful, and scientists still don't know what happens to matter when they're pulled into them. The universal idea, however, is similar to the trampoline analogy. Eventually, all matter will be drawn into a deep and black abyss. Although the concept of black holes has been around since 1783, it wasn't until 1967 that the term was officially used. Many consider John Mitchell to be the theoretical progenitor of black holes. In tight orbits with stars, he speculated, these unseen but gravitationally powerful objects would be discernible. In the 1930s, after Mitchell's groundbreaking discovery, theoretical researchers tested the black hole hypothesis using Einstein's general theory of relativity. They proved that stars with enough mass may collapse under their own gravitational pull, creating black holes. When astronomers Paul Merton, Louise Webster, and Thomas Bolton saw a huge invisible object 6,000 light-years away in the early 1970s, it confirmed Mitchell's prophecy. The first black hole ever detected by humans was this object, which was nicknamed Cygnus X1. Although these mysterious beings are invisible to the human eye, this new information proves that they may be discovered. Black holes are based on an astonishingly solid scientific basis. Our current best guess is that our Milky Way contains up to 400 million of these objects. It has also come to light that supermassive black holes are located at the center of at least 2 trillion galaxies in the visible cosmos. It is now believed that hundreds, if not thousands, of these enormous supermassive black holes reside in regions of space where several galaxies coexist. The awe-inspiring size of this celestial event makes us wonder about the universe's many mysteries. We can only speculate as to what further mysteries black holes may conceal in light of the tremendous power they possess. A black hole is a celestial body with an extremely high density and a massive mass that causes it to exert a strong gravitational pull. Even light is unable to escape their grip due to the immense strength of the energy. At their centers, spiral and elliptical galaxies have black holes, according to modern scientific theory. Black holes may be classified into 3 different types. We find stellar mass black holes, the tiniest kind, in one group. Its mass ranges from 100 to 1,000 times that of our Sun. Their formation is caused by the supernova explosion that usually occurs when the core of a large star collapses. Supermassive black holes are at the other extreme of the spectrum. These celestial behemoths may have masses millions, if not billions, of times greater than our Sun's. According to the standard explanation, these enormous objects acquire their massive mass via absorbing nearby stars and merging with other black holes. Middle of the spectrum are the mysterious intermediate mass black holes, of which there have been only a small number of confirmed cases. Between 100,000 and 100,000 times the mass of the Sun is where intermediate mass black holes are located. The supermassive variant is thought to have originated from these basic components, which merge in the end. Not only can black holes shed light on the mysterious orbits of individual stars and the Milky Way galaxy, but they also reveal a new frontier in the physical sciences. According to general relativity, Einstein's theory of relativity, mass warps space and time, causing gravity. Because of their very high density of mass, black holes have an extraordinary gravitational pull. But as we get into the singularity, the center of a black hole, the complexity increases. The scientific world is still split on what exactly transpires in this mysterious area, since the gravitational forces are so overpowering. It would seem that matter's information is erased as it is pulled into a black hole, according to Einstein's general theory of relativity. But such annihilation is theoretically impossible, according to quantum mechanics. Consequently, black holes provide a fascinating and intricate theoretical domain for mathematicians and astrophysicists. Nowadays, a lot of people are trying to figure out how to make these two ideas work together. Black holes provide a one-of-a-kind opportunity for scientists to test the most basic hypotheses about how the cosmos works. All the way to the complex world of string theory, these questions touch on quantum physics, general relativity, and other related fields. Black holes are different from ordinary holes, despite popular belief to the contrary. Alternatively, a black hole may be thought of as a powerful magnet. However, its attraction is not limited to metals, but extends to all kinds of matter due to its immense gravitational pull. Every time we take a jump, the force of gravity keeps us from soaring into space. While Earth's gravity is always drawing us in toward its core, it stops acting once we're on the surface. Unlike Earth, a black hole doesn't have any surface to slow you down and has a gravitational pull that's far stronger than Earth's. The feeling of falling into a deep hole is hence the inspiration for the name of these things. The collapse of a massive star due to the pressure of gravity compressing all of its matter into a very small volume is a well-known process that produces a black hole. An object's gravitational attraction is proportional to its mass. If you think about it, when we speak about gravity, it's not only Earth pushing on you, your own body also pulls on Earth to a lesser extent. This is mostly due to the fact that planets are far heavier than Earth. Due to the Moon's lower mass compared to Earth, the gravitational pull is reduced, which is why astronauts seem lighter on the Moon. Could you please explain what black holes are if they are not just holes? From a purely mathematical perspective, they occupy a spherical-shaped three-dimensional space. The event horizon is a hypothetical border that connects the singularity at the center of a black hole to the rest of the object. The central singularity is so dense that it defies scientific description. It also has no physical volume and pulls all stuff in its vicinity with its immense gravitational force. The basic characteristics of black holes are defined by their essential nature. In theory, this point is both very dense and infinitesimally tiny. To provide an example, think of how, similar to being at the North Pole, the northern hemisphere X tugs at you more forcefully than the southern hemisphere. Because the strength of Earth's gravitational pull changes as one moves away from the planet, the amount of force you feel is not constant. There is a stronger draw on the components that are nearest you and a lesser influence on the faraway ones. Nonetheless, keeping the masses constant, gravity would be amplified to an enormous degree if this mass were enclosed in a somewhat smaller volume. What differentiates a star from a black hole is its density. Gravity is amplified, and mass is concentrated when there is density. A black hole's event horizon, a black circle in space, is a common visual representation in film and art. In encircling the core singularity, It serves as a border or point of no return. At the moment it crosses, it immediately draws all matter to the center core. It requires more substance, even if it seems like a solid border or edge. To put it another way, black holes are not physical things per such, but rather areas with a very low density of matter. All matter is contained in the central singularity, but all surrounding space is empty black hole, because everything that tries to enter is instantly dragged in and merged with the central singularity. No amount of light can escape a black hole's tremendous gravitational pull. Because of this, it is not feasible to watch them closely. Instead, gravitational wave detectors and enormous radio telescopes are used by the scientific community. Albert Einstein postulated in 1915 that objects in motion cause ripples to form in the fabric of space-time, thus fusing the two dimensions of space and time around them. The effect is analogous to the ripples that propagate over a pond's surface. The Laser Interferometer Gravitational Wave Observatory, LIGO, made a groundbreaking discovery in 2015, 100 years after its inception. For the first time, they picked up on gravitational waves. About 1.3 billion years ago, two black holes collided, leading to this remarkable finding. Black holes may now be located by observing the effects they have on their immediate surroundings. As they draw in gas, dust, and stars, they heat them to very high temperatures, which causes them to release observable radiation as heat. The Event Horizon Telescope accomplished a great deal in April 2019. The telescope is an intricate network of 8 radio telescopes on the ground that were built to take pictures of black holes. In the galaxy Messier 87, which is part of the Virgo galaxy cluster, it captured the first ever picture of a black hole and its shadow. The picture shows a bright ring around the 55 million light-years distant black hole, which has a mass 6.5 billion times that of the Sun and is 55 million light-years from Earth. As matter is drawn inward by the black hole, this radiant ring is a representation of the thermal emissions from superheated gas that is whirling about the event horizon. When people learn about black holes, they often wonder what secrets they hold. But it's not a good idea to attempt to get inside one. No matter how enormous the black hole is, the results aren't good. Make the leap into a stellar mass black hole. A transformation known as spaghettification would take place in your body. It seems hilarious, but it's really rather serious. A horrible destiny awaited you, as the enormous gravitational pull of the black hole will ensnare you from head to toe, twisting you into a spaghetti-like shape. Contrarily, a supermassive black hole such as Sagittarius A** may be the best option if you choose to investigate black holes in order to gain scientific understanding. It has an incredible 4.31 million solar masses, is around 44 million kilometers wide, and is located in the core of the Milky Way. While astronomers Robert L. Brown and Bruce Balick made the 1974 discovery, it wasn't formally named until 1982. When you reach the event horizon, the last barrier to entry, you will have entered Sagittarius A**. From inside, you could see the outside world, but no one else could since all the light you emitted would be contained. The bright side is that you won't be turned into spaghetti, since the stretching tidal force isn't as great as the gravitational pull of supermassive black holes. But stay on the edge of your seat. Unless the white hole hypothesis has any promise, there is no way out. To put it simply, white holes have the ability to discharge matter somewhere if black holes eat it. Through a wormhole, which connects dimensions, these two distinct concepts become one. Black holes have the potential to become white over billions of years. Be patient, however. If you were inside, the operation would be completed in a fraction of a second, and time would fly by. This is all very theoretical, however, and scientists are always working to improve upon it. Were we to enter a black hole and do research to add to humanity's knowledge base, it would be a hypothetical but intriguing thought. It's not always true that all stuff in a black hole is compressed into an infinitesimally tiny ball at its center. On the contrary, it might condense into the most compact possible arrangement of matter contained in an extremely small space. Within the context of loop quantum gravity, this hypothetical object is envisioned as a Planck star, and very theoretical strategy for developing a quantum gravity equivalent is loop quantum gravity. This idea divides the cosmos into little, independent pieces by quantizing space and time. Because these pieces are so little, our regular movements seem unbroken. One benefit of this level of space-time granularity is that it avoids the creation of singularities inside black holes, which is in line with the goals of quantum mechanics. Another is that it gives a natural explanation for gravity. The discrete character of space-time prevents matter from compressing farther than the Planck length, an extremely small value at around 1.68 x 10 circumflex 35 meters, when it is crushed by the immense gravitational pressure of a collapsing star. Everything that goes into a black hole is squished into a very tiny ball, yet not infinitesimally tiny. Although explodes may be too harsh a word, the material finally expands again as a result of its resistance to further compression. Thanks to this procedure, black holes become ephemeral things. From where we are in the cosmos, it takes billions, if not trillions of years, for black holes to undergo this process because of the tremendous time dilation effects in their vicinity. Another idea that tries to do away with the singularity without using quantum gravity theories that haven't been verified is the gravastar. Although it may seem like a collection of astronomical backyard components, it isn't always the case. The matter contained therein is the primary differentiator between gravastars and black holes. A gravastar is full of dark energy, as opposed to a black hole which contains a singularity. The expansion of our universe is being propelled by a mysterious element known as dark energy, which exists in both space and time. This isn't some made-up cosmic event. It's real and contributes to the speeding up of the universe's expansion. Gravastars have so much dark energy that stuff that falls on them stays on the surface instead of penetrating the event horizon. It is believed that gravastars resemble regular black holes in appearance and behavior. A black hole's event horizon is an important limit that marks the end of the road, so keep that in mind. In this place, not even the light itself is safe. On the other hand, new data from gravitational wave observatories, like Virgo and LIGO, especially during black hole. The presence of gravastars has been called into question due to mergers. Gravastars are in a precarious position due to the growing number of observed cases, since combining them would result in signals that vary from those of merging black holes. Although gravastars and Planck stars seem interesting, they aren't the exclusive hypotheses being considered. A less unconventional, but more grounded in realism and complexity, theory of black holes has been put forward by scientists as an explanation for singularities. Our knowledge of non-rotating uncharged black holes, which may be somewhat dull, gives rise to the idea of a singular point with infinite density. The truth is that black holes, particularly when they spin, may display much more interesting properties. The singularity expands into a ring shape while the black hole is whirling. If one were to traverse this ringed singularity in accordance with Einstein's general theory of relativity, they might potentially enter a wormhole and, upon escaping via a white hole, find themselves in a completely different and intriguing region of the cosmos. On the other hand, the stretched singularity's fast rotation makes the interior of a spinning black hole very unstable. In the theory of general relativity, the strong centrifugal forces produced by such a rapid rotation push instead of pull. As a result of the tremendous gravitational attraction, radiation from beyond the area is pulled inside, creating an inner horizon within the black hole. The anti-gravity effect does, however, drive radiation away from the ring singularity. An important tipping point is the inner horizon. An extraordinarily powerful and energetic radiation storm would greet you should you cross paths with its inner horizon. It's as if the whole history of the universe were suddenly revealed to you in the space of a single eye blink. Since we see black holes in our cosmos that are spinning, the emergence of this inner horizon further complicates our knowledge of these objects. This provides further evidence that something out of the ordinary is occurring, and that our mathematical models may be incorrect. However, a new idea called gravitational waves has emerged, and it has shown us how black holes work on the inside. One of the most incredible and dramatic events in the cosmos, black hole mergers may one day be better understood thanks to this new study that might shed light on the complex mechanisms involved. Scientists made history in 2015 when they made the first detection of gravitational waves. The use of large and precise instruments allowed them to accomplish this accomplishment by studying the space-time ripples caused by black hole collisions. The cosmos is shaken to its very core by the reverberations of these cosmic collisions. Using this technique, scientists have now discovered over 100 newly formed black holes in the universe by gravitational waves that have propagated across space and time. In order to illustrate this process, scientists use the analogy of shaking a container and inferring its contents from the sound it makes. Here, two black holes collide, causing the ground to shake and the sound to be the gravitational waves that they release. A recent research has used these findings to improve models of cosmic events. Researchers are trying to comprehend how these phenomena function and test how well Einstein's general relativity holds up in harsh conditions. Scientific models had, up until recently, depended on linear interactions, which were useful but limited since they didn't take nonlinear behavior into consideration. Nevertheless, recent studies on nonlinear interactions have the potential to improve models by as much as 10%. Furthermore, this study will help us find additional black hole collisions in the future, which is a huge step toward being ready to detect gravitational waves in their next stage. We will get a better understanding of gravity and other cosmic phenomena as a result of this development. Since 2020, the LIGO Observatory has been inaccessible because of the epidemic. It was the first facility to detect gravity waves. Nevertheless, new technologies are expected to become up in the next several years, offering the chance to see black holes in more detail. Once again, we appreciate you tuning in. You may see more mind-blowing videos like this one by clicking the video on your screen while you are still here.